Hello, everyone. Let's go ahead and get started on this section, fundamentals of hypothesis testing. So hypothesis testing is our basic way that we are testing a statistical hypothesis. Revolutionary, I know. And it is tying together all the things that we have done in our previous sections and chapters into a nice little bow. So let's go ahead and discuss, what do we do when we are attempting to test a hypothesis? So the first thing that we do is we state the null and alternative hypotheses. Our null hypothesis is given by H naught, and our alternative hypothesis is H sub alpha. This is also sometimes given as H sub 1. Okay. We then determine which distribution to use for our test statistic and state the level of significance. So this is basically, we need to find which distribution will work for our given context. So like our Z, our T, our F, etc. And then gather data and calculate the necessary sample statistics, and then draw a conclusion and interpret the decision. So let's go ahead and get some basic definitions down here. So hypothesis testing is a statistical process for determining the likelihood that a given hypothesis is true. The alternative hypothesis is a mathematical statement that describes a population parameter, and it is the hypothesis that the researcher is aiming to gather evidence to support. This is also known as the research hypothesis. The null hypothesis is the statement that expresses the value currently believed to be true. It will always be a statement of equality. So if we want to know whether or not it is different than a particular value, then our null hypothesis would be that they are in fact the same. Okay. Now we are going to have different tailed tests. The tailed tests refer to our left tail, right tail, or what are called two-tail tests. And we'll get into that in a bit. But first, let's go ahead and just take a look at constructing null and alternative hypotheses. This one says, determine the null and alternative hypotheses for the following scenario. At Northwest Mississippi Community College, syllabi for an online class states that students should expect to spend 10 hours per week completing coursework for each 3-credit-hour class. The director of e-learning for the community college is concerned that students are being required to spend more than 10 hours per week doing work for each 3-credit course. Okay, so the director believes that they are spending more. That's what they want to test. That tells me that's what my alternative hypothesis is going to be. So my alternative hypothesis is going to be that my mu is greater than 10. Well, my null hypothesis is going to be that there is no difference. That is to say that it is equal to 10. Okay. So my null hypothesis, which I'm going to determine whether or not this hypothesis is false, and it is that mu equals 10, and this is mu is greater than 10. Okay, let's do another one. Incidentally, if you have mu is greater than 10, this would be a right-tailed test when we do that, but we'll see what that looks like in a bit. Anyway, after learning that Peter Collat of Switzerland could hold his breath for 19 minutes and 21 seconds underwater, a group of students decided to conduct their science fair project around the amount of time an average adult can hold their breath. Part of the group found research to suggest that adults can hold their breath for 30 seconds when submerged in lukewarm water. The other half of the group found evidence to suggest that the mean time is different when the water temperature is colder. The group would like to test this claim about adults holding their breath in cold water. Okay. So my alternate hypothesis here that I'm going to start with is that, well, is different. What that means is different is not equal to. Okay. So if I say it is different than that, I mean it is not equal to. And of course, our null hypothesis is that they are equal. Okay. Pretty straightforward stuff here. Okay. Then let's get some more pieces of terminology here. A test statistic is the value in a probability distribution used to make a decision about the null hypothesis. A sample statistic is said to be statistically significant if it is far enough away from the presumed value of the population parameter to conclude that it would be unlikely for the sample statistic to occur by chance if the null hypothesis is true. The level of confidence denoted by alpha is the probability of making the error of rejecting a true null hypothesis in a hypothesis test. Okay, so what does this mean? So what this means is we need to find a test statistic, which is to say a value that we are testing that we can correspond with something in our distribution in order to test. And our goal in this is to determine if this test statistic is going to be far enough away from our population parameter that we can say it is unlikely that it's that far away because of chance. Okay, now note, we're not saying whether or not it's true or false. We don't have enough information to conclude that. Rather, what statistical testing is it is a test for determining for a given level of significance, otherwise sometimes referred to as a level of confidence, perhaps a confidence interval, that it is due to chance. So if I say 95%, what I'm saying is it is outside of the 95% confidence interval. So I could say with 95% confidence that it would not be due to chance. Okay, that's what we're testing when we're looking at these. Okay. And again, something to note, we are not testing whether the hypothesis is true or false. That is not what statistics does. Statistics is saying to a given level of confidence, whatever that level of confidence you're looking for is that inside or outside of that level of confidence? Now, for the purposes of our textbook, it's usually going to be 95% or 99% or 90%, one of those sorts of things, but that's not always the case. For say physics, for example, in order for something to be determined to be a discovery, what that means is that it is 5 standard deviations away from the presumed parameter characteristic. That is to say, it is 0.000003 away. Okay, this is also sometimes referred to as greater than 5 sigma. So a bit of a fun little physics thing is the Higgs boson's existence was proved, and the way it was delivered to Higgs, that's the Higgs boson had been discovered, was that it was determined to within 6 sigma. So that means that it was outside of that by 6 standard deviations. So to a sufficient level of confidence to the physics community, that was not due to chance. Okay, that's the sort of thing that we're getting at here. Again, we are not looking at truth in statistics. We are looking at probability of truth. Okay, so note that don't oversell what you're doing and don't misunderstand what we're doing. Okay. So what are some conclusions for a hypothesis test? We can reject the null hypothesis, or we can fail to reject the null hypothesis. Note, we are not accepting the null hypothesis. We are either rejecting or not rejecting, which is not the same as accepting. Okay. 2 potential types of statistical error are a type 1 error. This is also known as an alpha, when one falsely rejects a null hypothesis that is true, or beta, a type 2 error, when one fails to reject a null hypothesis that is false. Okay. Generally, we view type 1 errors to be worse than type 2 errors. The most common example that you'll see in any statistics textbook is it is worse for a society to jail an innocent person than it is to have a guilty person free. So that's the sort of thing that you should think of. We are going to be testing alpha statistical errors in this. Okay. But let's go ahead and take a look. The campaign manager for a gubernatorial campaign believes her candidate connects with a younger audience and will connect with a younger audience. Oh, I got a bit of a typo. We'll ignore my typo there. With a younger audience and will draw a larger vote turnout for the 18 and 24-year-old demographic. Historically, only 25% of eligible voters between 18 and 24 years old vote in the election. A hypothesis test with a 5% level of significance is performed on the manager's claim. The result is to reject the null hypothesis. Does the conclusion support the manager's claim? So, as a reminder, and I'll just note what my null hypothesis and my alternative hypothesis is. My alternative hypothesis, this is what I want to prove, or what I want to show is true. And it is that they connect and will draw a greater turnout. That is to say that my turnout average mu will be greater than 25% or 0.25. My null hypothesis is that mu is going to equal 0.25. Okay. If we are rejecting the null hypothesis, then what that means is that we will be accepting our alternate hypothesis. Okay, so this does support our claim because I can reject this null hypothesis here. Okay. Let's do another example here real quick. Based on historical data, the Board of Education for one large school district believes that the percentage of high school sophomores considering dropping out is at least 10%. A high school counselor in the district claims that this percentage is too high. A hypothesis test with alpha equals 0.02 is performed on the counselor's claim. The result is to fail to reject the null hypothesis. Do the findings support the counselor's claim? So here's the thing. We are not rejecting the null hypothesis, so that indicates that we do not support the counselor's claim because we do not have enough evidence to reject the null hypothesis. And as a reminder here, my alternate hypothesis, we're looking at a proportion here. So that's P is less than 0.1 is my alternative hypothesis because 10 is too large. And my null hypothesis is that P equals 0.1. If we do not reject my null hypothesis, that means we cannot conclude this H sub alpha, and thus it does not support this claim. Okay. Let's go ahead and do another one. A television executive believes that 99% of households in the United States have at least one television. An intern at the executive's company is given the task of using a hypothesis test to determine whether the percentage is actually less than 99%. The hypothesis test is completed, and based on the sample collected, the intern decides to fail to reject the null hypothesis. If in reality 96.7% of households own a television set, was an error made? If so, what type? Okay. So let's go ahead and take a look here. We are noting that so we failed to reject the null hypothesis. So let's start with our null and alternative hypotheses here. My alternative hypothesis is that it is less than 99. And this is P equals 0.99. And we know that actually P equals 0.967. So we actually do know that it is less than that, but didn't know that when we're doing this. However, based on the sample collected, the intern decides to fail to reject. So they do not reject the null hypothesis. Well, we note population is less, so it should have been rejected. However, they did not reject. So if you fail to reject when you should have, remember that is our type 2 error. Okay. And again, you can think of it like we should have convicted someone but did not. That is to say, a guilty person is free. That's a type 2 error. Okay. Let's do one more here. A study regarding the effects of television viewing on children reports that children watch a mean of 4 hours of television per night. Kiko believes the mean number of hours that children in her neighborhood watch per night is not 4.0. She performs a hypothesis test and rejects the null hypothesis. Assume that in reality, children in her neighborhood do watch a mean of 4 hours of television per night. Did she make an error? If so, what type? So Kiko believes that it is not 4.0. That is to say, my alternative hypothesis is that mu is not equal to 4.0. And that means, of course, that our alternative hypothesis is that that our null hypothesis rather is mu equals 4.0. Okay, so my alternative is it's not equal. My null is that it is equal. And we know that in actuality, mu equals 4.0. And here, Kiko decided to reject. So Kiko should not have rejected. Kiko did reject when she should not have. That is to say, she convicted someone who was innocent. That is a type 1 error. And again, that is generally viewed to be the worst error to make. Okay. Hopefully this makes sense to everybody here. Now, unfortunately, the thing about statistics is that when we are making these sorts of analyses, we usually don't know what the parameters are. We're attempting to figure out what they are. So usually we actually can't tell whether a type 1 or type 2 error has been made. In these examples, they gave us the population parameters. Usually we don't know what they are, however. So do be aware, we don't always know whether or not we've made a type 1 error. And that's an unfortunate thing, but that's simply true in the world of applied statistics. But anyway, let me know if you have any questions as you're going through these or want to see any additional examples. Otherwise, I will see you in the next video.